To finish up today, let's go ahead and do an oblique shock reflection problem. Now, I just want to stress here that shock reflections are very, very complex, especially if two shocks hit each other. There is a lot of crazy stuff that can happen. And oblique shocks don't have to reflect off walls. They can actually reflect off just simply boundaries. Like if you have a rocket nozzle, you will actually see the shocks reflecting off of the air itself. So it's not something that comes just because of a boundary. It's not like a mirror. It's not like a sound wave bounces off a wall. It is there because the flow is required to turn for whatever reason, and the shock wave must result because of that. So we can only usually do very simplistic versions of this, but it gives you an idea of why it's there, what's going on there. But for more complex examples, you would probably have to do some sort of simulations. We always come back to simulations eventually. So with that being said, my little caveats for all this, let's draw it out and do another problem for it. So I have my wind tunnel, or whatever it is. It looks something like this. Beautiful, I'm loving it. It's looking good. So we have a deflection angle right here, and that's going to be equal to theta 1. Going to cause an oblique shock. That oblique shock is going to then reflect. And so this angle right here will be beta 1, and this angle will also be beta 1. And we're also wondering what this angle right here is, which we gave the term phi last time. So my flow is going to have a Mach number of 1 right here. Then it's going to turn. I have a Mach number of 2. And it's going to be forced to turn once again to have a Mach number of 3 so that it can continue straight along this pathway. Will there be other stuff happening? Most definitely yes, 100%. But we're not seeing that because I've truncated it before the craziness begins, okay? Before the craziness begins. So let's give our values. So our Mach number is going to be equal to 3.2. My pressure is going to be equal to 25 psi absolute. If you're wondering, no, English units, remember that everything with shock waves is always ratios, so units are completely moot. It doesn't actually matter. I mean, it does matter for your value, but we don't have to do any conversions or anything else, which is glorious. It is so nice. Okay, and we're going to have a turning angle of 17 degrees. Cool. So let's begin. First thing we're going to have to do is figure out what is beta 1. Okay, what is beta 1 equal to? Question mark. That's for a Mach number that's equal to 3.2, and that's for theta that's equal to 17 degrees. So let's bring in our handy dandy tool, which is to go to that theta beta Mach diagram. So I know where it is now. I can jump to it much more quickly. Right here. Scroll down just a bit, section 9.2 in your textbook. It might be in the appendices as well. I've never been sure about that. And here it is. So I'm just going to copy it in like I did last time and deal with it inside. There we are. Okay, so I have a deflection angle of 17 degrees, and I have a Mach number of 2.4. So first I'm going to trace the 2.4 line to make it easier for myself to see. Here is 2.4, and so this is the one I'm tracing. Okay, that looks good. And now, let's go ahead and figure out what happens for 17 degrees. So first off, to help you out here, I want to draw. This way, which is halfway, that is 18. So 17 must be halfway again, so that is 17. So there's each of these little lines is half a degree. So I'm going to go straight up. There are so many lines right there. There we go. Oh, that looked like it intersected pretty much right on the line there. I'm pretty happy with that. Mach number of, oh, why did I say 2.4? Did I say 2.4 earlier? It's 3.2. What am I doing? That was the last problem. Sorry, I'm remembering the numbers from the last problem. The 17 degrees is correct though, okay? I did that fine. Just, I actually read our problem statement. I would have seen that it was this one. Still looks good, still intersected fine. I was just way off, and there we go. Okay, sorry everyone, jumped around there. Now, so each of these steps on the bottom is half a degree, or half a degree. Over here it's 1 degree, so that's 31, 32, 33. Okay, so what is beta 1? It's 33 degrees. I know that now, I can solve for everything else. So beta 1 equals 33 degrees. Okay. Now, if we're going to find everything else, we're going to have to go to the appendices. I'm going to the appendices. I have to find the normal component of my Mach number, because that's the only way the normal shock tables work, right? Only way they're going to work. So let's get that done. So M1 normal is equal to M1 sine of beta 1. When there's a beta 1 now, when I haven't been using the 1s, it's because we have a reflected shock. We have a second oblique shock here. I have to deal with both of them. And once we get to expansion fans, I'll do some much more complex problems that use both shock waves and expansion fans. And there is a whole ton of stuff you can do there. And we'll have a lot of fun with that, or not so much fun, but we're gonna do it regardless. You're required by law. Didn't realize there was law in here. Yeah, that's true. Yeah. So 3.2 sine of 33 degrees. Okay, and what does that come out to be? That comes out to be 1.742. So that's what I'm going to use when I go to Appendix B. Now, I've been jumping to Appendix B a whole ton, and also I don't want to have to interpolate. I've shown you interpolation once today. If you know how to do it. So I'm just going to give you the values here, and we can go from there. You might get lucky and find, I think in the Feroki textbook, that actually has 1.74, and so you can use that much more easily. So what I will find if I go to Appendix B, and likely interpolate or use the equations, is that M2 normal is going to be equal to 0.630, and that P2 over P1 is going to be equal to 3.37. Okay, so we've got that. But if I'm going to get to this reflected shock wave, I'm going to deal with it. I have to figure out what beta 2 is, and this right here, that is beta 2. Okay, that is beta 2. And if you're wondering, what is? Make sure I'm doing this right there. Turned it down, turns it up. Yep. Oh, no, I failed you there. I'm sorry. That was the wrong line. So what is beta 2 going to be? It is, trying to draw this nicely. That's the second Mach number. This is my direction. I have to be turned this way. There we go. So this would be beta. My deflection angle would be theta. And this angle right here, I'm still doing it wrong. I just want to fail myself. Oh, it is frozen on me. Give me a second. Okay. So, trying one more time to draw this properly so I don't make some horrible mistake. This angle right here, that is this guy. This one right here, that is theta. There we go. That did it right. And this angle right here would be beta. So this is theta right here. That is beta. There we go. I got it all now. Just had to put my angles in the right places so I didn't make a horrible mistake. Beautiful. But this one right here is not beta 1, it is beta 2. I have to figure out what beta 2 is. And I do that in various ways. So what I'm going to do is I'm going to do it by first figuring out what my Mach number is. I've got to figure that out after the shock wave. I have to know what M2 is, and I can go to the tables and figure out a lot of the rest. So M2 is going to be equal to my normal Mach number after the shock wave over sine of beta 1 minus theta. So that would be equal to 0.630 over sine of beta 1, which is 33 degrees, minus theta 1, which was equal to 17. And if I plugged in my calculator, I would get 2.29. So that is my actual Mach number after the shock wave. Nice. Happy days. Okay. So once again, my flow is going to have to be turned, though, because it's currently heading down at an angle theta. It has to be turned, so it's now going horizontal afterwards. This is M3. We have this reflected angle right here. We have our shock angle right here, that's beta, and this one right here is our deflection angle as well. Okay? And it's the same angle because it's being turned back to horizontal. It was horizontal, it turned away from it, it's turning back to it. It turns by the same amount. So a lot of that is simple to find, but not everything is. Like, I know that from this, that theta 2 is going to be equal to 17 degrees. But what is beta 2 going to be equal to? What is that actually going to be? To figure that out, I go back to my handy-dandy theta beta Mach diagram. I'm going to just say 2.3 to keep myself from going absolutely bonkers. I think that's fine. Okay, so I'm going back over here. As a note, there is no 2.3, but I'm just going to say like halfway in between these two is good enough. And so we're going to go up to about here. I'm going to go over and get the value, which is 42 degrees. And I completely eyeballed that. Just so you know, the exact value, if I had done it perfectly, was 42.2. So really just saying, it's about halfway between, works. Now I'm going to go with 42.2 because my numbers are 42.2, but you can see there that I got it close without really having to do that. And sorry, I was probably going too quick. You can write that down if you need to. Or...
No, okay.
Cool. Okay, so beta 2 is actually equal to 42.2. We got that from the theta beta Mach diagram. Okay, so with that, we have to find our normal Mach number for this second shock wave. Remember, that's not the same as the normal Mach number coming out of my first shock wave. It's different. And so this, M2n for the second shock wave over here, what is M2n, is going to be equal to M2 sine of beta 2. That'll be equal to 2.29 sine of beta 2, which is 42.2 degrees. And so with that, I would get that my second normal Mach number is going to be equal to 1.54. Okay, where do we go? We go to the appendix again. So we go back to appendix B. In this case, 1.54, you probably still need to interpolate. It might give you 1.5, 1.6. By the way, you're probably going to have to interpolate. So either interpolate or you will use the equations. Whichever is easiest for you. If you got a good calculator, if you got a good idea of how to plug things into Excel, use the equations. Otherwise, probably don't. Won't be helpful for you. So from that, for a normal Mach number that's equal to 1.54, I get that my normal Mach number afterwards is going to be equal to 0.688, and my pressure ratio of P3 over P2 is going to be equal to 2.59. There we go. So let's figure out the last few details. I need to figure out what Mach number 3 is. It'd also be good to figure out what my pressure is after all these shock waves. So M3 is going to be equal to M3 normal over sine of beta 2 minus theta 2, which is just the same as theta. Yep. So that would be equal to 0.688 over sine of 42.2 minus 17, which is 1.615. So even though I've gone through 2 shock waves so far, I am still supersonic. I'm still supersonic. So that's the magic of oblique shock waves. I'm increasing my pressure dramatically, but I'm supersonic still at the end. Okay, the last question I might have is, well, what is P3? What is the pressure after all these shock waves? That's going to be equal to P1 times P2 over P1 times P3 over P2. So that's going to be equal to, let's see here, my initial pressure was, I believe, 25 psi absolute. And then P2 over P1 was 3.37. And then P3 over P2 was 2.59. So it gives me a pressure in the end of 218 psi absolute. Not quite a factor of 10, but still a great increase in pressure. So if I was using this as a compressor, it's working pretty well. And things like this are used for compressors. Okay, so we found our Mach numbers, we solved everything inside this reflective section, and we figured it all out. So that's it for today. Thank you.